Hello everyone, welcome to lecture 9. And this lecture is going to be on section 3.3 in the textbook, which is on rates of change and behavior of graphs. So rates of change and behavior of graphs. Okay, so I want to start off by defining what's called the average rate of change. So the average rate of change, you can think of it as the change in output over the change in input. So average rate of change I'm going to abbreviate this as AROC, just so I don't have to write average rate of change all the time. This is going to be defined as the change in output over the change in input. Okay, so typically we call the output y and the input x, right? So I could also define average rate of change as delta y, right, change in y over delta x. But remember, delta y is y2 minus y1, and delta x is x2 minus x1, right, where we have points x1, y1, and x2, y2. Or I could also write it like this. Instead of y2, I could call it f of x2 minus, instead of y1, I can write this as f of x1 over, and then the denominator is the same, x2 minus x1. So you may recognize this, right? So the average rate of change is basically the slope of the secant line that connects those 2 points, right? So if you were to graph this and connect the 2 points, and you basically what we're doing is calculating the slope of the line that connects those 2 points. Okay, so let me give you an example. I'll start off using a table, and then we'll get into graphs. So let's say you're told that the table below gives the annual sales in millions, right? So millions of dollars of a product. So here's the table. So the first row is, let's say, the year, and the second row is the sales. Okay, so if the year is 1998, the sales are 162 million. If the year is 1999, sales are 189 million, and so on. Okay, and then 210. All right, so let's say you're asked based on that table, what was the average rate of change of sales between 1999 and 2000? So what was the average rate of change of sales between the years 1999 and 2000? Okay, so maybe the easiest way to do this is to actually list the two ordered pairs, the 2 points. So in 1999, the sales were 189 million, right? So 189. So think of this as like, I'll call this the time. So this is like T1, and then this is maybe like S1 for the sales. So think of the year as being like my variable T, and sales is like S. And then for 2000, I have the ordered pair 2000 corresponds to sales of 210. So this is kind of like T2, S2. So then the average rate of change is going to be S2 minus S1, right? Change in the output over T2 minus T1 over the change in the input. So in this case, it would be 210 minus 189 divided by 2000 minus 1999. So this turns out to be 21 over 1, which is equal to 21, right? And it has units. It's 21 millions of dollars per year. So millions of dollars per 1 year. Right? It's always, the average rate of change is always going to be, it's always going to have units of, in the numerator, it'll be the units of the output, and the denominator will be units of the input. Okay, what about, so same question, we're referring to the same table, but let's say now I want to know the average rate of change between 1999 and 2004. So again, if we look up those values in the table for 1999, that again was 189. So think of this as T1, S1. And then for 2004, the corresponding sales was 234 million, so 234. So this is T2, S2. So the average rate of change is going to be S2 minus S1 over T2 minus T1. So it'll be 234 minus 189 over 2004 minus 1999. And that turns out to be 45 over 5, which we can simplify to 9, right? 9. And again, it's $1 million per year. Per year. Okay, so that's all you really need to do if you're asked to find the average rate of change on, say, given some information in a table. Let's say now you're given the information using a graph. So let's say we want to find the average rate of change on the interval -2, 3. Okay, so we want to find the average rate of change on the interval -2 to +3 using this graph. Well, if we look at the coordinates for at -2, the coordinates are going to be this point right here, right? So it's going to be -2, 1. So you can think of that as sort of like x1, y1. And then at 3, represents this point, which has coordinates 3, 3. So this is like x2, y2. So again, what I'm doing really is finding the slope of the line that connects those 2 points. And that will be my average rate of change. Okay, so let's calculate now. So average rate of change, it's going to be y2 minus y1 over x2 minus x1. So in this case, y2 was 3 minus y1 was 1 over x2 is 3 and x1 was -2. So then this is going to be 2 over 5. So 2/5. And again, it's nothing more than the slope. I'll write that down here. This is just the slope of the line segment connecting those 2 points. Should capitalize that. Okay, so the average rate of change is really just a slope. All right, let's do it now where we're given the equation itself. Go to another page. So for example, let's say I want to find the average rate of change of this function, f of x is equal to 7x cubed plus 6 over x squared on the interval say -3 to 3. Okay, so this is sort of like my x1 and my x2, right? If I want to use those are like the x coordinates of those 2 points. Okay, so average rate of change, I want to write it in this form now, right? It's going to be the function evaluated at x2, that's like my y2, minus the function evaluated at x1, that's like my y1, over x2 minus x1. So this would be the function evaluated at 3 minus the function evaluated at -3 over 3 minus -3. Okay, so we need to figure all these out. So let's do the function evaluated at 3. Well, I go to my function where I have an x. I'm going to substitute in a 3. This is going to be 7 times 3 cubed plus 6 over 3 squared. Well, this turns out to be 7 times 3 cubed. 3 cubed is 27, and 7 times 27 turns out to be 189. Plus, and then 6 over 9, right? 3 squared is 9. 6 over 9 is the same as 2/3. If you want to simplify this further, you can rewrite both of them, right? If I multiply by 3 over 3, so I can rewrite both of them with the same denominator. So this turns out to be 567 thirds plus 2 thirds, which is 569 thirds. Okay, what about f of negative 3? Well, it's going to be the following, where I have an x, now I plug in negative 3. Remember, this whole thing is being squared, right? So now, negative 3 cubed is actually a negative 27 times 7, so this is a negative 189. Plus, but then it's 6 over 9 again, so that's still 2 thirds. So this is going to be, I guess it'll be a negative 567 over 3 plus 2 thirds, which is a negative 565 thirds. Okay, so now we can actually find the average rate of change. So it'll be f of 3, which we found to be 569 over 3, minus f of negative 3, which we found to be negative 565 thirds, over 3 minus a negative 3. Okay, so if you work this out, it turns out that numerator is simply going to be 378. Denominator, of course, is 6. And then 378 divided by 6 is equal to 63. So that's the average rate of change, 63. All right, let's do another graph one. Find the average rate of change of f from 1 to 4. And let's say the graph looks like this. So this is x, this is going to be y, or this, I'll write it as f of x in this case. So this is 0, 1, 2, 3, 4, 5. And let's say it does this. I'll do it in red. So something like that. It's hard to draw this. Well, there we go. Okay. So what is the average rate of change from 1 to 4? Well, let's look at what's going on at 1. When x is 1, what's y? It looks like y is also 1, right? So this is the 0.11. And at 4, if 4 is the input, what's the output? What's y? It looks like it's 2, so this is 4, 2. So just call this, say, x1, y1, x2, y2. So the average rate of change is going to be y2 minus y1 over x2 minus x1. So it'll be 2 minus 1 over 4 minus 1. Well, that's going to be 1/3. Right, which, again, is also the slope of this line that connects those 2 points. Right? So the average rate of change is nothing more than a slope of the line that connects those 2 points. Okay, here's one more. Let's say you're told that r of t equals 2t squared minus 1 represents the position in meters of a particle at time t seconds. What is the average velocity over the interval from 1 to 3 seconds? So what is the average velocity over the interval from 1 to 3 seconds? Okay, so I'll give you a hint because you have to know a little bit of physics here. So here's the hint. The average velocity is equal to the average rate of change of position. You could even say average rate of change of position relative to time, or with respect to time, I'll say. With respect to time. Okay, so if I want to figure out the average velocity, that's just my average rate of change. So basically, I want to know the position at time 3 seconds minus the position at 1 second over 3 minus 1. So if we work this out, right, the position at 3 seconds. So I go to my my function, and where I have a 3, or where I have a t, I plug in 3. So in this case, I have 2 times 3 squared minus 1. Well, this is going to be, what, 2 times 9 minus 1, so that's going to be 17. And then I want r at 1 second. So now wherever I have a t, I plug in a 1. So this is just going to be 2 times 1 minus 1, which is just 1. And now I have my answer, right? So the average velocity will be 17 minus 1 over 3 minus 1. So this will be 16 over 2, which is 8. And in this case, there's units, right? Because it's a real physical problem. It's meters per second. So 8 meters per second would be my average velocity. Okay, so I think that's all I want to talk about, at least for now. We can do more of this in lecture if we need to. But now I want to switch gears and talk a little bit about looking at where functions are increasing, decreasing, and constants, looking at graphs of functions. I'm going to do this on a new page. So using a graph to determine where a function is increasing, decreasing, or constant. Okay, so let's say I have this graph. So this is my x. This would be my function. I'll just call it f of x. And let's say it does something like this. So it goes on forever in that direction. And then let's say it goes on forever in this direction. Okay, so there's a bunch of special points here first. So this point right here, this is what's called a local or relative maximum, right? Think of it as like the top of a hill. It doesn't have to be the highest point, but just locally, it's the highest point. So this is a local, or some people call it a relative maximum. So relative maximum. You can probably guess what this point is. This is a local minimum, right? So this was a relative maximum. This point is a relative or local, doesn't matter, minimum. So that point right there. And now, where is the function increasing or decreasing? Well, if you think about it, right, over this point, if I am moving, remember we're always reading, think of it reading as left to right, right? The x values are increasing. So here, the function is increasing, right? Then it's decreasing and then increasing again. So how do I know that? Well, think about what's going on here. I'll pick a couple of points. Let's say I pick a point A right here and then a point B. So it's increasing if f of B is greater than f of A, where B is greater than A. Do you guys see that? So like this point right here would be the point A, f of A. And this point right here would be B, f of B. And since B is greater than A, and we also see that f of B is greater than f of A, in fact, for any AB that I choose in that interval, right, if I choose any AB where B is always greater than A, then we find in this case that f of B is always greater than f of A. That means the function is increasing. But visually, it's where the function is rising, right? That means it's increasing. Okay, here would be decreasing. And what's going on here? Well, it's decreasing. And that means f of B is less than f of A, where B is greater than A. Do you guys see that? So if I pick any, let's say I pick this point right here as my A, and maybe this point right here is my B. Right? So this would be f of A, and then this point right here would be f of B. So B is greater than A, and we also find that f of B is less than f of A, therefore it's decreasing. In fact, for any AB that I choose on that interval, as long as B is greater than A, then if f of B is less than f of A, then we know it's decreasing. Right? But the easy way to think about it is if it's going down the hill, it's decreasing. And of course here again, it's increasing. Right, same as before, if f of b is greater than f of a, where b is greater than a, then we know it's increasing. And we can see that we're going up, right, up a hill, so it's increasing. Okay, the other way of thinking about the local maximum, local minimum is the following. So you can define a local maximum as being where the function changes from increasing to decreasing. And then local minimum is where the function changes from decreasing to increasing. Okay, and again, you can see that here, right? So here the function's increasing, and then it decreases, right? So local maximum is where it changes from increasing to decreasing. It's the point where locally you have a hill. And then local minimum is where the function goes from decreasing to increasing. So it's where it changes. And locally, think of it as a place where you have a valley, right? It's the bottom point of the valley. So top of a local hill is a local maximum, and the bottom of a local valley is a local minimum. Okay, so here's a question. Where is the function increasing, decreasing, or constant? Okay, so if we look at this graph, where is the function increasing, decreasing, or constant? So it starts from, let's say it starts from negative infinity, right? It's dropping, so it's definitely decreasing over this interval. And it switches from decreasing to increasing right here. So it looks like we have a local minimum at this point right here. Right, so it's a local minimum at -3, -2. Then it increases. What's going on here? So between the interval 1 and 3, it stays at an output of 3, right? The y value is 3. So therefore it's constant, right? So it's constant over that interval. And then after that, it again is decreasing. And let's assume it goes all the way to positive infinity. Okay? So basically, to answer this question, it would be the following. It would be decreasing from negative infinity to -3. Now, you don't want to include -3 itself, that point, so I'm going to use parentheses, because right when it's a local minimum, it doesn't make sense to say whether it's increasing or decreasing. So always use like parentheses when we're talking about intervals where it's increasing or decreasing. And then where is the other interval? Well, union, and then remember with some 3 to infinity. Where is it increasing? Well, it looks like this function is increasing from -3 to 1. So -3 to 1. And again, I'm going to use parentheses. And then finally, it's constant from 1 to 3. Right, so it's constant 1 to 3. Okay. What about, let's go back to our toolkit functions, and for each function, let's say, where is it increasing or decreasing? Let's list all the intervals for the toolkit functions. Okay, so toolkit functions. So you guys should be pretty familiar with these by now, right? So toolkit functions. All right, so remember the first one was a constant, like f of x equals c. Remember that looked something like that, right? It's a horizontal line. So in this case, it's neither, I'll just do an up arrow for increasing, nor decreasing. So it's neither increasing nor decreasing. The next toolkit function was the identity. Remember that was f of x equal x, and that looked like this. So for that one, I would say it's increasing over all real values, right? An entire real number line. So from -infinity to infinity, it's increasing. Then we did, let me try and keep the same order, absolute value. So absolute value function. Remember that was f of x equals absolute value of x. Or we could also write it as a piecewise function, but I'll just write it like this for now. So that looked like this. So in this case, it's decreasing from -infinity to 0, and it's increasing from 0 to infinity. Okay, then we had quadratic. So that was f of x is equal to x squared. So that, remember, was a parabola. So like this. So in this case, it's decreasing from -infinity to 0. And it's increasing from 0 to positive infinity. Right, and in fact, in this case, there's a local minimum at x equals 0. It also turns out it's a global minimum. We'll talk about that in a little bit. Okay, cubic function. So that was f of x equals x cubed. So remember that was like this. Kind of gets flat there. So this one's increasing, right, over the entire interval. So it's increasing from -infinity to infinity. Then we had reciprocal. That was f of x is 1 over x, right? Or x to the negative 1. I'll just leave it as 1 over x. That looked like this. It was like a hyperbola, right? So here it's actually it's decreasing from negative infinity to 0, but it's undefined at 0, so the union. And again, it's decreasing from 0 to infinity. Then reciprocal squared. So f of x equals 1 over x squared. So that was like this. So in this case, it's decreasing 0 to infinity, and it's increasing from negative infinity to 0. Then we had the square root. That was f of x equals the square root of x, or x to the 1/2, right? You could write it both ways. That looked like this. So in this case, this is increasing from 0 to infinity. And then finally, we had the cube root. The cube root function, which was f of x equals the cube root of x. And that looked like this. Something like that. So in this case, it's increasing, right? Again, over the entire interval from negative infinity to positive infinity. All right, great. So those are all the toolkit functions. Now, there's one last thing I want to mention, and it's what's called absolute maxima and minima, or some people call them global maximums and minimums. Okay. So absolute. Again, some people call these global maxima and minima. Basically, maxima and minimum are the plural of maximum and minimum. So maxima and minima. So let me give you the definitions, and we'll do like a simple graph to explain this. So the absolute maximum of f at x equals c is f of c where f of c is greater than or equal to f of x for all x in the domain of f. So basically, it's going to be the highest point, right? The highest point if you look at the entire graph. And then the absolute minimum of f at x equals c is f of c where f of c is less than or equal to f of x for all x in the domain of f. Okay, so let's do one quick example. If we look at this graph, let's say we want to locate the absolute maximum and the absolute minimum. So if you look here, right, there's a bunch of relative maximums, right? There's a relative maximum there, there's a relative maximum there. But what is the absolute maximum? The absolute maximum is the largest value. So basically this point right here, that would be the absolute maximum. And the value is going to be 6.959, and the corresponding x value is negative 1.138. Okay, since it's the largest value of the graph, that's the absolute maximum. Then again, there's a few relative minimums, right? We have a relative minimum here. It looks like it's at the bottom of valley, another one here at the bottom of the valley. But the absolute minimum is the lowest point. So this is a little bit higher, right? So it's going to be right here. And that point has coordinates 2.004 and negative 4.502. So the absolute minimum is negative 4.502. And it occurs at the x value of 2.004. Okay, so absolute maximum, absolute minimum of the entire function. All right, great. So that's it for this lecture. The next lecture we'll talk about combining functions in a special way, which is called a composition. So we'll talk a little bit about compositional functions, like a function of a function. Great, thanks.